to my third and last lecture. I will talk today about, or continue talking about dense matter and then talk about neutron stars. But again, if you have any questions, just interrupt me and yeah, ask straight away. So yesterday we talked about this, right? So we have dense neutron matter. We describe it in terms of the energy per particle as a function of baryon number density, and from this we can calculate all important quantities that we'll need later on. We have, like, the baryon density is the number of nucleons per volume. The energy density is its product times the energy per particle, and then the pressure would be the slope. And then I talked about all of this. We have these two systems, symmetric matter, pure neutron matter, and the difference is the symmetry energy. And then we can describe it in terms of these parameters and model the equation of state in terms of these parameters. And if we want to use our microscopic theory to calculate these systems, right, we will use some solver to calculate either these parameters or basically these curves directly. Okay, so actually this was one of the exercises yesterday, but since we didn't do it, I just wanted to flash it here. So the most simple system that you could imagine to model, let's say, neutron stars is a free Fermi gas. So you just have the nucleons, they don't interact, they build a Fermi gas, right? And basically then each single particle state, so each nucleon carries a momentum and it has a spin component and an isospin, so it could be a neutron and a proton, and it can have spin up and spin down, right? So there are basically four possible configurations. And then if you want to calculate the number of particles, you just sum this up, or you make an integral out of it and do the integration, and in the end you will find that, okay, your particle number is given by this, so the volume times this GST, which basically just counts how many degrees of freedom you have. So if you have only neutrons, you have 2 spin configurations, so this would be 2. If you have neutrons and protons and 2 spin configurations, this would be 4, for example. So you just plug this in, and then you get the density. And you can do the same for the energy, and you will get the energy per particle, which is just 3/5 times the Fermi energy in a free Fermi gas. And then you can, in principle, here you could plug in the density, and you will see that the energy per particle of a free Fermi gas goes as the density, okay, goes as the density to the power of 2/3, basically. Okay. So basically, that's the simple most model for the equation of state, right? You have non-interacting system. If you want to add interactions, it becomes a bit more complicated. And so I do not really want to talk about many-body methods in detail, but I still wanted to add them to the slides for you to look at later on if you want to. So there's one approach that people use, which is called many-body perturbation theory, which is used by these people and some others. And it's basically a diagrammatic approach formulated in momentum space, and you basically sum these weird-looking diagrams. So basically you have the kinetic energy, which is just an integral of the momenta, so basically what you have seen before. That would be the free Fermi gas, in principle, if there was no interaction. And then you have these first-order interaction terms, where you integrate the momenta of the particles. So these loops mean you integrate over the system. And you get first-order contributions. You can have second-order contributions where particles interact twice, and so on and so forth. So you can build these diagrams up order by order in this many-body approach, and then you plug in your chiral EFT Hamiltonian, and you get out your energies. And so this is how basically, if you look at this leading order, sorry, it's not leading order, first order in perturbation theory, where I said you sum over these states, you can basically write it like this, and these sums become integrals over the momentum in the end, and then basically you just evaluate this equation and you get your first order energies per particle. Good. And you can then put in like your 2-body force, 3-body force, 4-body force, whatever you want. It really is very simple and straightforward. Second order is more complicated, so you have to have you basically integrate now over these states between these these insertions of the interaction. But in the end, you can just put in your potential into these equations, and you get your second-order corrections. And then basically this would look like this if you write it in if you translate the sums to integrals again over the Fermi sphere, it would look something like this. So it's already much more complicated than first order. Current calculations using perturbation theory go up to 4th or 5th order, so you can imagine that these things become much more complicated very fast. But in the end, this is a very simple approach to calculate the equation of state of nuclear matter, and if the interaction is perturbative, so basically related to what we have seen yesterday, if the short distance repulsion is very weak, the interaction is usually perturbative, and if it's perturbative, you can use perturbation theory to a certain order and get a good description of dense matter. And here you see some results. We have talked about, I've shown them yesterday, so basically this is the equation of state of pure neutron matter and the equation of state of symmetric nuclear matter at 2 different orders in chiral EFT using this many-body perturbation theory approach. And you see you get these curves, you get some uncertainties, and you can use this to constrain these parameters that I talked about yesterday. So the symmetry energy is in a certain range, which would be the difference of this and this. And this L parameter is the slope here. It's in a certain range. And then you can see order by order, you can calculate these quantities. And then you could in principle, use them to plug into any approach that you want. And similarly, you can look at different proton fractions. So here you see proton fraction 0, so x equals 0. That's pure neutron matter. This is symmetric matter, and this is something called asymmetric matter, and here it has a proton fraction of 10%. And then from blue to green, you see what happens if you increase the temperature, right? So this is the free energy now, not the energy per particle. So the free energy is the energy minus temperature times S, the entropy. So basically, if you increase the temperature, right, you lower the free energy, but generally you can calculate any thermodynamic configuration, any density, temperature, proton fraction, you could calculate with this approach very, very easily. Okay, then there is another approach that I quickly wanted to mention, which is the one that I usually use, which is the quantum Monte Carlo approach. You actually have heard about this in the colloquium yesterday. So quantum Monte Carlo is a very precise method to calculate the properties of strongly interacting systems like atomic nuclei and dense nuclear matter. And basically, you rewrite the Schrödinger equation as something like this. So you start from some trial wave function, and you evolve it in imaginary time. So this is basically just time evolution on the trial wave function, and you will project out the ground state. And the reason this works is that if you expand the trial wave functions and eigenfunctions of the Hamiltonian, which I call here phi I, and you put this operator there, you will suppress any contribution that has an energy larger than the ground state. And so over time, the system cools into the ground state. And the ground state is the only thing that survives. And then you have your particles distributed according to the ground state wave function, and then you can do any calculation you want for the ground state. And usually you solve this integral by splitting it into many, many, many small time steps, and then you can solve every time step using Monte Carlo integration techniques, which is why it's called quantum Monte Carlo. So it's quantum because it solves a quantum problem, and it's Monte Carlo because it uses Monte Carlo integration, and then that's it, basically. And so, I'm sorry, that's a very bad-looking animation, but it still tells you what happens. So you put particles in a box, you move them around, and you measure the energy at every time step. And okay, this is just one box, so one walker, if you're aware of Monte Carlo integration. So this is why the noise is pretty high. But you see that the trend is that the energy decreases over time, right? So you just make your moves, you measure, and you find the system cools. If you do this not just with one box, but one walker, but you use many, many walkers, a statistical ensemble of walkers, you will find something like this. So that's now for the deuteron. You see, you start out somewhere very high, and then over time, your deuteron cools into the ground state. And there's some noise because it's a statistical method. Sure. About the movie, okay. Very good.
I noticed that the neutrons are not moving much, only in the local limit. Is it true? I mean, I thought that if you have 14 neutrons, it scatters like this.
Oh, so
It's not like this, but it's just oscillating locally.
I mean, they do a random walk, right? First of all, what you see is, so here you see you come down and you are there, right? What I show you is already somewhere in this phase, first of all. So there is not much change of the configuration. But then, sorry, you also, I mean, first of all, it's a 2D projection of a 3D box, so it's already very difficult to see how they move, right? Because they could move into the plane. But this is already more or less equilibrated, so they will not move that much, but they still move, and they, I mean, you make small time steps, right? This is for, I don't know how many time steps, but you make small time steps, so if I showed you this video for a much longer time, they would move much more, of course. But yes, and I think, yeah, you had a question. Yes. So, not in my movie because it's not great, but here you see this. So, this is just the first 600 time steps. If you continue, it will level off. So what you see here, these are the Monte Carlo points, the measured energies, whatever. And then you see the exact result as a black line, and after convergence, the quantum Monte Carlo average as the blue band. And you see it converges onto I mean, there's an uncertainty, statistical uncertainty, because it's a statistical process, but it will converge to the true number. But it's very expensive. So it's usually very precise. You have very low uncertainties, as you can see, but it's also very expensive. So if I wanted to calculate the equation of state, it cost me 1 million CPU hours or something per Hamiltonian. Well, but there is a move. So there is a move made of the neutrons. You put neutrons in a box. You sample the positions for each walker. You have a configuration of neutrons, and then you make small time steps and just accept them or refuse them based on some Monte Carlo criterion. So you really move the neutrons, the positions of the neutrons, the walkers around. Yes, but then you have 10,000 walkers or whatever. Yes. Yes. Yes, there is a path. It's a random walk, but yes. So they move. Why wouldn't you? So I think the question is, why do you go below this? It's not variational. So there is a variational Monte Carlo that obeys the variational principle, but quantum Monte Carlo doesn't have to, due to some ways how it's set up. It has to do with the nodes of the wave function. To mediate the sign problem, but you can go below the experimental number. Sorry, that's for 1 Hamiltonian. So that's not the black is not the experimental line. The black is the exact result for this Hamiltonian. And this Hamiltonian overbinds the deuteron. It's just an example. Thank you, good question. Any other questions? Okay, so here you see the same but for neutrons. So again, the points, the red are the points, and if you do the running average, you will get this green band, and you see it converges at some point. And then that's the energy per particle for neutrons at this density. And so, okay, this we have seen. I just added this slide because I wanted to go back here to this point, because someone asked yesterday, why is this description so bad? So, okay, you start from a trial wave function. That's what you have to do you asked the question, right? Yes, okay. So you start from the trial wave function that you have to guess. That's an educated guess. And then you evolve the trial wave function in time. And you will go to the lowest energy state that is included in the trial wave function, right? So if you expanded it, if the real true ground state would not be in the trial wave function for some reason, you wouldn't go to the real true ground state, but you go still to the lowest energy state in the trial wave function. For carbon-12, this trial wave function has to be built out of hundreds of Slater determinants, and the computational cost is proportional to the number of Slater determinants. For the calculation you see, I think it was 150 Slater determinants that are included in this, but you would need more. But so it's basically your trial wave function isn't good enough to really bring you to the true ground state. But the best trial wave function that was studied in this paper brings you here. But this is just a very complicated atomic nucleus. Oxygen-16 has 1 Slater determinant. That's okay. But this one is complicated. So this is maybe the most expensive calculation on this plot, even though it's not the heaviest system. So this is why I wanted to show this. But then, okay, here you can see the energy per neutron as a function of density, and the symmetry energy as a function of density, and in red is the quantum Monte Carlo result. Ignore the gray bands. ask me later if you want, but ignore them for now. So you see you can calculate this equation of state of pure neutron matter order by order, and you get your uncertainty bands for the equation of state. And then you can compare this to many other approaches. So this is like a plot by someone from Darmstadt, and she collected many different results, as you can see here. And on the left-hand side, you see the energy per particle in neutron matter, again, as a function of density. And on the right, you see the pressure coming from these bands as a function of density. So that's the derivative of this. And you can compare all these different approaches, and you see, well, there are some differences from approach to approach, but generally they predict something that is very similar. So the energies in the density range are more or less, they are overlapping. The pressures are more or less overlapping. Maybe some uncertainties are larger than others because of the way things are implemented or some peculiar choices that were made. But generally, everything agrees, right? Korolev gives you on average one band for the equation of state. And so you can use this to understand astrophysical systems, for example. Okay, there's another calculation, maybe a more recent comparison between different bands, but still nothing really changes, right? You have some differences, but overall everything agrees quite well. So now I want to apply this to neutron stars. But before, is there any other question to dense matter, to nuclear matter? Mm-hmm. Okay, so there's basically you can think of if you had a unitary system, right, or a system that is that only has infinite scattering length S-wave interactions at every density. You can think of this as maybe a lower bound to pure neutron matter, because S-wave interactions are weaker in pure neutron matter, so it would be more repulsive. D-wave interactions are more repulsive, and three-body forces are all repulsive. So you could conjecture that if you had a unitary gas at all densities, it would be a lower bound to the interacting system, the real interacting system. And this is why it's plotted here. It's just a comparison. So basically, most calculations are above this, right? They do not violate this bound. So you can use it and just compare and use it as a lower bound, basically. We thought about this. I don't think that's possible. I mean, maybe. I don't think you can. It depends on which density regime. I mean, you could maybe have an upper bound in some density range, but generally I think upper bound is difficult. Because, I mean, maybe the non-interacting gas, right, you could think of as an upper bound. If you knew that overall all interactions would be attractive, but this would only work where you're not too high in density. But then the free gas would be an upper bound. On the energy, not on the pressure. The free gas has a lower pressure, but it has a larger energy. I don't know I don't know if you know, but the free gas would go up here and live somewhere up here. And at some point, it might intersect the interacting band. But yeah, anything else? Yes. So, I mean, so quantum Monte Carlo is actually good for every system, but you have to have a good ansatz for the trial wave function. So that's where all the magic happens. If you have dense neutron matter, the trial wave function is the single particle states are basically plane waves. So you have a Slater determinant of plane waves. That's very easy. You can do a great calculation. For nuclei, the trial wave function is much more complicated. If you want to do some, I don't know, BCS stuff, right, you have to put pairing in your trial wave function. As long as the trial wave function knows about the important features of the system, you can do a good, or can get a good description of the system. But you have to get a good trial wave function. So that would be the drawback, if you want. But generally for matter, it's simple. It's a simple system in principle, right? And so you can do a good description. Okay, anything else? Otherwise, I talk about neutron stars. Okay. Cool. So neutron stars. Anyways, most interesting topic. So neutron stars. Who of you know? I don't know. Works with neutron stars, on neutron stars, or knows about neutron stars? Okay, one. Cool. Good. Then I'm very happy that I can talk more about them. So you could think, what do we care about neutron stars? I told you they are the densest object in the universe. So why do we think, right, that they are very useful for nuclear physics? I mean, they are stellar objects. We usually look at atomic nuclei that are very small. So what's the point? But as I also told you, the matter in neutron stars is nuclear matter, right? It's determined by the strength of nuclear interactions. And so neutron stars can help us answer questions like what are the relevant degrees of freedom at high densities in QCD, right? Because if they are realized in nature anywhere, they will be realized in neutron stars. That's the densest system. So if we have like exotic matter, free quarks, a quark, like quark matter or somewhere in the universe, it will be in the core of a neutron star. And then we can use the properties of neutron stars, as you will see, to determine the interactions between these degrees of freedom. And so neutron stars are basically a laboratory for nuclear physics in the cosmos that probes the highest densities we can probe, far beyond anything, far beyond in density anything we can probe on Earth, and at isospin asymmetries that we cannot realize in the lab, right? Because here we can only collide atomic nuclei, they are almost symmetric, so whatever comes out is almost symmetric. But this is 95% neutrons, so it's really, really, really isospin asymmetric. And so the idea is we start from some nuclear forces, we do a many-body calculation, we calculate the equation of state and nuclei, and then we can learn about the nuclear forces. But we can also use Bayesian inference of the equation of state from astrophysical data, predict the properties of neutron stars, and compare to this data, and then learn about the nuclear forces. So this is the loop we would like to do. And then neutron stars are interesting because, as I said, they have these high densities, and they are extreme in any regard. So they do not only have the highest densities in the cosmos, they also have extreme magnetic fields. Because they have high densities, they have extreme gravity. They can spin extremely fast. I mean, they are of the mass of our sun, or heavier, between 1 and 2 solar masses. But the heaviest neutron star spins like 700 times per second. So that's insane. I think this is super cool. And then the densities are just to maybe... I think it's usually, if I tell you, the density is 10 to the 14 grams per cubic centimeter. No one really knows what that means. And I try to come up with an example that maybe helps, but I think still no one really knows what this means. But if you take an iron block with 1 centimeter side length, you would have to press this to the size of a bacterium to get to the densities in a neutron star. So it's insane. And like 1 tablespoon, people always say 1 tablespoon of neutron star matter weighs as much as all the humans that have ever lived or something like this. I don't know. It's very incredible. And the neutron stars they look like an onion, basically. They have this weird onion-like structure that you can see over here. There's some atmosphere around the neutron star, which is like mostly hydrogen. But then if you go down into the star, you increase density, and you have like an outer crust, which is ions, neutron-rich atomic nucleons or ions in a lattice, in a Coulomb lattice. In the inner crust, you suddenly get a fluid, a superfluid of neutrons that drips out of these nuclei. Then the outer core, all the nuclei dissociated, and you have a fluid of neutrons and protons. So this is very close to the neutron matter I talked about, or nuclear matter I talked about. And in the inner core, we really don't know what's happening there. There could be quark matter. There could also only be neutrons and protons. There could be hyperons. Anything that theorists can make up that could be stable in nature could be in the core of a neutron star. So yeah, as I said, we don't know what's happening here, but what I talked before, like chiral EFT and our calculations tell us something up to the properties of the outer core of a neutron star. So if you wanted to model the neutron star, of course, it's not just nuclear theory. As I said, strongly interacting matter is mainly in the core, right? So this is where nuclear physics really contributes. But if you wanted to model properties of these other phases or these other layers of the neutron star, you would need many different types of physics. For instance, if you want to model the emission of some electromagnetic radiation from the neutron star, you need to know atomic physics, plasma physics to really model this. And that's really a complicated problem, right? But for whatever I talk about, I only focus about the strongly interacting matter part down here in the core. And as I said, because they are so extreme, the information they provide is complementary to any laboratory experiment we can make. And so it's really crucial to observe these objects if we want to learn about interactions, nuclear interactions in certain regimes. Okay, and I want to give a short history of neutron stars because I also think it's very, very, it's very nice and very cool. So yeah, so I will talk about it. I told you in my first lecture that in 1932, the neutron was discovered. And without knowing that there are neutron stars, without knowing yet the engines of supernovae and so on and so forth, right? We didn't know really anything because we didn't know neutron stars exist. But there were these two astronomers, Walter Bade and Fritz Zwicky, who were at, I think, Caltech. Actually, yeah, they were at Caltech. And they, like a year after the neutron was discovered, proposed in this paper basically the supernova engine, right? So they say, with all reserve, we advance the view that a supernova represents the transition of an ordinary star into a neutron star, consisting mainly of neutrons. Such a star may possess a very small radius and an extremely high density. A neutron star would therefore represent the most stable configuration of matter as such. It's just theoretical reasoning. It's correct. And I think, again, this is a fascinating example that theory can predict things that we later see experimentally or observationally. Then, 5 years later, 4 or 5 years later, 5 or 6 years later, there was the first calculation of the properties of a neutron star by these 3 gentlemen. Actually, these 2 and this one did it independently, but they derived the so-called Tolman-Oppenheimer-Volkoff equations, which are the stellar structure equations in general relativity that you would need to solve to describe the structure of a neutron star. And you will see them later, but it's not really important here. But they derived these equations, and they solved for the properties of a neutron star, and they found that the maximum mass that a neutron star could have is 0.7 solar masses. And they used what we derived before, this free Fermi gas of neutrons. That was the equation of state they used. And so they published this paper where they said, we have seen that for a cold neutron core, there are no static solutions for core masses greater than 0.7 solar masses. It seems unlikely that static neutron cores can play any great part in stellar evolution. So they were wrong. So sometimes theorists also make mistakes. And I guess you know already now which mistake they made. Can anybody guess? No? They used the free cold degenerate neutron gas. There are no nuclear interactions in the neutron gas. Nuclear interactions are important to describe neutron stars, and so they made the mistake by simplifying the equation of state. And this is why they found this too low maximum mass. And so for many, many years, no one really, I think people believed them, and no one really thought there are neutron stars. Until in 1967, there was a young grad student, Jocelyn Bell, you see her here, who built, together with her advisor, radio telescopes. That was her PhD thesis. And she looked at the data, and she found basically this. So there was the signal, and every 1.3 seconds or so, there was a blip. There was a blip. So it's a very regular signal that they found. And so it came from, obviously from some astrophysical object, or some object out there. They coined it little green men, just to be funny, I guess. I don't think they really believed they are aliens, but they found it remarkable that it's so precise. And so, this frequency doesn't really change over a long time. It's really, really accurate. It stays 1.3 seconds. And so people thought, what could that be? And the only thing that they came up with, if it's a stellar object and it can spin with one spin per second, it needs to be something very compact. And so they deduced that it's a neutron star, and then neutron stars can basically beam radiation like this. They are then called pulsars. And if one of these beams hits Earth, then you see basically once a rotation period, you would get a signal, and this is how you see the neutron star rotate. So basically as this pulsar. And so her PhD advisor won the Nobel Prize for this discovery 7 years later, sorry. But then in the same year, there was also a double pulse. The first double neutron star was discovered. It's called the Hulse-Taylor pulsar. It's a binary neutron star system, so you have two neutron stars that orbit around each other. And this allows tests of general relativity because these stars are general relativistic objects. And if you plot, so here this is the shift of the periastron time. So I don't know how many of you know what that is, but it's one of the predictions of general relativity, and it's basically if you have an orbit of a star and another star, and it's slightly elliptic, then this thing will move over time. So the periastron is the closest distance, right? So that would be the periastron. And over time, this will shift around, and so your ellipsoid moves around the central object or whatever. So that's a prediction of GR. You see the line, that's the calculation that you would do with GR as a function of time. And in black, you see the data points that you observe from the system. And they fall right on each other. And there's actually a more complicated, more interesting plot where you have like 6 different GR predictions, and they all intersect in one point. And so it basically means that GR describes this system extremely precisely. And so far, no one looking at these found any deviation from the predictions of general relativity. So that's one of the most amazing tests of general relativity. And so this is why there was another Nobel Prize in that discovery, so the second neutron star Nobel Prize. And then in 2000, in the last 1.5 decades, we discovered 2 solar mass neutron stars. So compare this to what Oppenheimer predicted. It's really, there's a huge difference, and this is all nuclear interactions. So these 2 solar mass neutron stars are the heaviest neutron stars we have seen. It doesn't mean there are no heavier neutron stars, but yeah, that's, as I said, the heaviest we have seen. And then in 2017, for the first time, we observed merger of a neutron star binary system in gravitational waves. I have shown you the video in my first lecture, and I think you will see it soon again. And there was another Nobel Prize, and it was not for the discovery of the 2 neutron stars, but for the discovery of gravitational waves. But still, I think maybe one can claim it for neutron stars too, a little bit at least. But yeah, so that's the history of neutron stars so far, and I think it's really fascinating. So there, I promised you this video again. So binary neutron star mergers. As I said, we have discovered the first of those in 2017. We have discovered another one in 2019, and since then we have not seen anything. But basically, neutron stars, as I said, are remnants of supernovae. They have these masses typically, and right then, if they orbit around each other, they emit gravitational waves, and at some point, the system will collide, and you have a kilonova. And so for this first observation that we made, we could see all of these signals. We did not just see the gravitational waves. We saw this kilonova. We saw actually a gamma ray burst coming out of the system. And we really observed the light curve and how it died down over many weeks, months, years. So we have a lot of data. So if you basically look at this, this is an optical picture of this merger. So this is when it happened. There was suddenly a blue blip appearing next to this galaxy. A few days later, it was red, so it was something that changed color on the order of days. We saw the gravitational wave signal. So this is the time until merger, and this is the frequency of the gravitational wave. And here's basically this frequency spectrum. And actually, think about what you see here. In the last 10 seconds, the frequency of the gravitational wave is 50 hertz, which means these neutron stars orbit around each other at least 25 times per second. There are 2 stars, heavier than 1.5 times the mass of our sun, going around each other in an orbit 25 times a second. That's mind-boggling. It's amazing. It's one of the most energetic events in nature, and so that's why they are so really cool. Yes?
There is another limit for the energy of the particles that comes out of this explosion. Can be TV or people have seen these things under the explosion.
We have not seen particles from there. I mean, this happened 40 megaparsecs away. You will see waves from there, right? Like light and gravitational waves. But if you wanted to see particles, it would have to happen much closer. Yeah. Oh, yeah. There is a picture of the photons that we have seen. So we saw a gamma ray burst. So gamma rays are Yes, I mean, there might be something with higher energy, but I think, yeah, most gamma rays is the highest that we have seen. Yes, but still, yeah, that's an amazing thing. Okay, and then there's another observatory that also provided us with interesting information, which is called the Neutron Star Interior Composition Explorer, NISAR. It's like this thing is as large as a washing machine. It's on board the International Space Station, and it's basically an X-ray telescope looking at rotating neutron stars and trying to measure the X-ray emission of these stars. And I will talk a little bit more about how they use this to constrain properties of neutron stars later. But yeah, so basically there's a lot of data. In addition, I don't show everything here. There are like radio observations. There are other X-ray observations that are not done by this telescope. There's a huge amount of data, but all of this tells us a bit about neutron stars. Because we have our equation of state, which now is given in terms of pressure as a function of density. And here you see like some equation of state models. And you see that neutron stars can explore densities, let's say up to, I don't know, 5 to 10 times nuclear saturation density. And in all of these different regions, right, we can try to constrain the equation of state. At low densities, we use Korolev-T to calculate the equation of state, but then gravitational waves from the in-spiral of these neutron stars tells us something at these densities. The mass measurements tell us something at the higher densities. And then so the post-merger phase, so after the two neutron stars collided, we have the densest objects in the universe, so they tell us something about the highest densities, right? And so if we puzzle all of these pieces together, we can try to identify which of these lines are more probable than others. So what is the equation of state of neutron stars? Okay, so how do we do this? So if we want to solve for the properties of a neutron star, we need to solve, as I said, the Tolman-Oppenheimer-Volkoff equations, and you see them here. There's actually a second equation, which is just the mass as a function of radius, but it looks very similar to standard stellar structure equations. But this one is the standard equation with some GR corrections that you see here. It's always the second term in these parentheses. These are corrections coming from general relativity. But if you solve this differential equation, you basically get the distribution of matter inside a neutron star. What you need to do this is, so you have here, let's say, the pressure as a function of radius. So radius is your integration variable, and the pressure is what you want to find out. But you do not know what epsilon is, the density. So you need to somehow relate pressure and energy density, and that's exactly what the equation of state does. It relates pressure as a function of energy density. So if you know your equation of state, you plug this into the Tolman-Oppenheimer-Volkoff equations, then what you find is the mass as a function of radius for neutron stars. And so this would work like you choose a certain central density in the neutron star, you integrate this equation up to this density, which gives you a certain mass and a radius. And you do this up to a different density, which gives you a different mass and a different radius. And if you do this, not infinitely many times, but if you do this many, many times, up to different densities, you will map out this curve, right? And so this curve we can observe, this curve we can calculate. But the correspondence between these curves is 1-to-1. So if we know this curve, we know the mass-radius relation. If we measure this to arbitrary precision, we know the equation of state. And this is how we can relate our interactions to the neutron star observations. And also I want to say, so this is only pressure as a function of energy density. We yesterday talked about temperature. So technically you could think temperature is also important. But for most neutron stars, they have temperatures of 10 to the 8 Kelvin, which sounds hot. But if you calculate the thermal energy, it's 8 keV. The Fermi energies in the system are 50 MeV or 30 MeV or something, so it's much, much larger. And you can just say, if I treat the neutron star to be 0 temperature or 10 to the 8 Kelvin, it doesn't really matter. It's the same, so you usually can ignore temperature. And then you really just need pressure and energy density. And so you saw already the mass-radius relation is complicated. For regular stars, right, it's very easy. It's basically a hot ideal gas because it does fusion. So if you measure stars, you measure their masses and their radii, you put them on a curve, it's pretty linear, pretty boring. For neutron stars, that's a small subset of possible equations of state that exist in the literature. And you see there's a huge uncertainty, right? We don't know what the equation of state of neutron stars really is. At low densities, so low mass, large radius means low density. At low densities, most of these curves collapse to some band with small uncertainty, and this is where we can do experiments, right? These are the low densities we can realize in the lab. But if we go to higher and higher densities, there is a large uncertainty. There are many different models that describe neutron stars. We do not really have precise data points, so we have this large uncertainty. And this is basically a reflection of the fact that we don't know what happens in the core of a neutron star. If there are quarks, you have, I don't know, some equations of state like this, I think the CM or whatever, it has quarks, right? They do this weird behavior. If you have only nucleons, you find something that goes up pretty fast. We don't really know, and so we have to somehow do a good job in theory to constrain what these curves would be, and we have to do a good job in data analysis of astrophysical data to see what these curves would be. Yes?
There are three curves on the left.
Yes, okay. Yes, the SQM is strange quark matter. It's basically a strange quark. I mean, it's just on this, I didn't make this plot. It was made by some other people in Bonn, I think. But yeah, if you put these strange matter curves there, in principle, so if you measured a star of 1.4 solar masses at this radius, right, you could technically describe it as a strange quark matter object, but I don't think that many people would believe that. But yeah, it's just a different model. Excellent. I will talk about. Very good. Give me a few slides. I will talk about this. Okay. So if we want to describe neutron stars, we need to somehow describe the equation of state. And if we want to actually account for all of these facts, right, we need to have a very general. So if we do a Bayesian analysis of data, we need some prior for the equation of state. So we need to construct a prior for the equation of state. And this prior needs to be general. It needs to capture uncertainties we have from chiral effective field theory or whatever at low densities. It needs to be as agnostic as possible to any assumptions we could make at higher densities, so it should include different high density behaviors. And it needs to be easy to connect, to be connected to any data or theory calculations that we have, right? And so it is important to include this high density behavior because I told you before, you can expand nuclear matter in terms of these parameters, these nuclear empirical parameters. If you do this, here you see the variation of the mass radius curve if you only vary these parameters. And you see there's basically not much variation. Maybe most variation comes when you vary this L sim, but still the difference in radius is pretty small, right? So if the neutron star only had nuclear matter, this might be a good approach. But there might be other forms of matter, right? And you saw there was a wide range from 9 to 14 kilometers that we could have before. And if you only treated nuclear matter, you wouldn't be able to capture this in your analysis. So you would bias your analysis towards nuclear matter, and you don't want to do this. So you cannot only use this parameterization to describe the whole neutron star. And so typically what people do is they look at the speed of sound. So the speed of sound is the derivative of the equation of state, so yet another derivative. But then the speed of sound can have very different behavior. So we know the speed of sound at very large densities. This is from QCD. And we know the speed of sound at low densities where we can calculate, and then it can either go smoothly to this limit or it can do anything in between, right? This is what this figure shows you. So if we can use this, we know the speed of sound cannot be larger than the speed of light because then you violate causality in the neutron star, and that's not good. The speed of sound cannot be smaller than 0 because then your pressure would decrease with density and the star would not be stable. So the neutron star speed of sound has to be between 0 and 1. But typically you can use this and just make a set of equations of state. At low densities, we have our calculations of the speed of sound with some uncertainties. So that's fine. We know what happens here. Then there is some density where we transition to a model where we just draw curves in the speed of sound plane. Anything. Anything between 0 and 1 would be possible. Here you see 4 examples, I think, 4 different examples of how these curves can look. But basically anything in this gray box could be sampled. And this would basically be a prior that describes everything we know coming from nuclear theory and experiment, let's say, but is extremely general at high densities where we do not have any information. And so we can easily include new phases or transitions to new phases of matter in an approach like this. And basically, that represents a way of extending uncertainties to larger densities, because we do not make any model assumptions, right? It's very agnostic. The only assumption we make is that we can parameterize in some form the equation of state in terms of the speed of sound, which is a very, very valid assumption, I think. And so then, basically, how you can construct the equation of state, you can basically sample your, let's say, empirical parameters that describe the nucleonic part, and you can implement chiral-EFT constraints if you want to. And then this describes the equation of state, as I said, at low densities. Then at high densities, you do your speed of sound modeling, which gives you the pressure as a function of energy density, and also the mass radius curve, right? And you do this millions of times, or thousands, tens of thousands of times, and you get a large number of equations of state that you then could use in astrophysical analyses of data. And here I just show you like the prior on these different parameters, but you can look at this later. It's not really important now. And so if you do this, what you see is the following. So here on the left, you see pressure density, on the right, mass radius, and then gray are all the curves that in this particular, to make this plot, there were like, I think, 30,000 lines that were sampled. They are shown in gray, and if you put in your chiral-EFT constraints, the green ones survive. And so you see basically that chiral-EFT, maybe it doesn't do too much to tell you about neutron stars at large masses, right? But it tells you neutron stars cannot have too large radii. They have to have sufficiently low radii, because chiral-EFT wants the equation of state to be to have a rather low pressure at low densities. You cannot make it to these large masses, large radii. But then if you go to higher mass, chiral-EFT doesn't give you any information about this. And this is basically, we can understand this from what we talked about yesterday. If we go higher in density, you saw before that the Fermi gas, right? The density goes as the Fermi momentum cubed. So if you go higher in density, your momenta increase. If your momenta increase, you approach the breakdown scale, and at some point, chiral-EFT breaks down. So you cannot use it to describe the whole star, but it still gives you important constraints at low densities, and they relate into these constraints for the neutron stars. Okay, 25 minutes? Okay. So how do we now use observations to constrain this further? So basically, that's your question. So the first thing that one can measure are masses of neutron stars. For this, one uses pulsars mostly. So there's something called pulsar timing. So you measure how the orbital frequency or whatever changes as a function of time for the pulsar. So basically, you have your pulsar here, right? And here's the observer. And every few seconds, you get your pulse that goes to you. So now, that doesn't tell you anything about the mass of the neutron star, not at all. But if you have another star in the system, you can use something called Shapiro delay, which is extremely cool. So if we look at this system edge on, right? So basically, we look from here, here's the star. If there's another if there's another star orbiting around, let's say there's another star that goes around your neutron star, which would move in this in the orbital plane, like this, right? So you see really edge on the system. If the second star is massive enough, and it's here, the light that you will see will be bent towards you, right? The gravitational field of this star will bend the light. But if you look at this, the travel time here is slightly larger than if this star would be on the other side, the light would go directly to you. There's a time difference, there's a time lag. There's a delay of the radio signal we see from the pulsar. And that's the Shapiro delay. And we can actually measure this, and you see the figure here. So if you look at the Shapiro delay signal, if you're in the right orbital phase, you are 20 microseconds slower. And you see this. So suddenly the pulse is 20 microseconds slower. And you can use this to extract the mass of both of these objects from the orbital period and the Shapiro delay. So you have two unknowns. You have the two unknowns here, which would be the mass of the two stars. And this is how you can extremely precisely measure the mass of neutron stars. And this was what was used to observe these heaviest neutron stars. Yes. Light bending, yes. Yes. So the orbital frequency tells you something about the total mass of the system. And the delay that you measure here tells you about the companion. And if you have the total mass of the system and the companion mass, you know the neutron star mass. And if you do this, I mean, since you have a pulse maybe every few seconds, right, you can accrue a lot of data. And so you can very precisely measure the mass of these systems. Okay, so maybe that's not that precisely, but up here it's pretty precise. And here you see like a posterior on this. So that's really cool. And so with this, you know the maximum mass of a neutron star. And for instance, if you have your models, like these many different models I showed before for the equation of state, right, you now can formulate a likelihood that includes the information you have from these maximum mass observations. There's also an upper limit. I will not tell you where this comes from, but generally these observations gives you a lower limit. And if you plug this in, it looks green, no? I don't know. It should be gray and blue. I don't know why it looks green. But anyways, you basically constrain part of the equation of state. And what you see in the lower panel, it's the PDF of the radius. So in the beginning, we only used chiral FT. We made a flat prior on the radius. But you see that if you put the mass information in, you change this quite a lot, right? You now change what is the most likely radius for a typical neutron star, because you rule out some equations of state. So a mass observation alone, you don't even need to know the radius. If you have a lower limit on the maximum mass of the equation of state, it will tell you a lot about the equation of state. But it's apparently still not enough, right? There's still large uncertainty. So then another observation we can use is NICER, as I told you before. And so NICER is also pretty cool. I told you they look at a rotating neutron star and the X-ray emission of the neutron star. And usually what happens is that if you look at a neutron star and you look at X-rays, they're like hotspots. Let's say there's one here and there's one there. And so hotspot means there's a lot of X-rays coming out of this location. It's just the surface temperature is so much higher, this is where the X-rays come out. So now the star is rotating. And so naively, you would expect, at some point the hotspots are on the back side of the star, and at some point they're on the front of the star. So if my emission comes from both hotspots, if both of them are at the front, I get a large X-ray signal. If both of them are on the back, I get a slow X-ray signal. And if like one is in the front and one is still in the back during the rotational period, I get like an intermediate signal. And so you have the fluctuation of your X-ray flux, right? But now the cool thing is neutron stars are so compact that if they are very small, you see light bending again from the back side of the neutron star. So if you have a small neutron star and your hotspot goes to the back, you still see it. And if you have a large neutron star, you don't have that much light bending and your hotspot really goes away. So if you measure the X-ray flux as a function of time and you model the emission and whatnot, you can estimate how compact this neutron star has to be to give you enough light bending that you actually see the backside. And so you can do this, you measure masses and radii, and you get these posteriors. And now you say, uncertainty is still pretty large, but it's still a piece of information, and the more data you accrue, the better your modeling will be. So that's pretty cool. And also, even though the uncertainties are large, this is a cool approach to understand what the radius of a neutron star is, I think.
Ingo, so this is bounded by the gravitation?
Yes, and the gravitation of the star is proportional to mass over radius. So, I mean, yeah, yes, of course. You always use general relativity to understand neutron stars. I mean, you have to, right? Because they are so massive and so small, so you have to use GR. Okay, how they are made, or? Okay, so neutron stars have magnetic fields, right? And so you could think of, obviously they emit like electrons or stuff, right? So they move along the magnetic field surface lines, and where the magnetic field goes into the neutron star, a lot of particles hit the neutron star, heat it up, and you get a hotspot. And this is where the emission comes from. So basically, depending on your if you had a perfect dipole through the center of the neutron star, you would have two antipodal hotspots. If your dipole is shifted, you have hotspots somewhere else. If your magnetic field looks weird, you get some very weird hotspot configurations or whatever. But it's basically where the magnetic field enters the star and where all the particles hit the surface. So yeah, you can now combine all of these things, and you basically, here's this NICER measurement compared to all the other things that we discussed before. And now you see NICER wants the radius to be large, but it rules out all these equations of state that have a low radius, right? So it pulls the equation of state towards larger radii. But even though the uncertainty is large, together with the other pieces of information we have, right, it provides a better constraint. And now we know the radius of a typical neutron star should be around 12 kilometers, which is much better than what we thought if we only base our estimation on nuclear theory. But then there's the much cooler observation, I think, the one I already talked about before. So if you have two neutron stars that go around each other, they deform each other. They introduce tides in each other. And you can see this in this video. Maybe shortly before they merge, you see they deform a little bit towards each other, right? There's a tidal bulge, and then at some point they collide with each other. And this is when you saw the kilonova before. This is just in density, so this is why you don't see, obviously, a flash of light. But this is basically a very similar animation to what you have seen before. They go around each other, they merge, and then there would be the kilonova, or here something weird happens, a remnant forms that wobbles around, whatever. But so when they go around, as I said, they deform, which means the gravitational wave of one neutron star introduces a tide on the other neutron star. It's like tides on Earth, right? Like what we have with the ocean. Like what the moon does to Earth. It's the same what one neutron star does to the other neutron star. And this can be measured. It's imprinted on the gravitational wave signal as something called the tidal deformability. And it's like some higher order general relativistic effect that describes the emitted gravitational waveform. So you can measure this from the gravitational wave signal. But now this tidal deformability, which is called lambda, the tidal deformability of a star with a certain mass is correlated with the radius of a star of a certain mass. And this is just because if you have a very large star, it's very easy to deform. I mean, it's not very easy, but it's much easier to deform a very large star because it is so large. If you have a very small star, it's very difficult to deform the star because it's so compact and gravity really resists the deformation much more. So if you have a large star, you have a large deformability. If you have a small star, you have a small deformability. So if you measure this from the gravitational wave signal, you can infer the radius of a neutron star. And so LIGO does exactly this. So the gravitational wave passes through Earth. We have this interferometer, right? And then once the gravitational wave goes through, you basically move the arm length in the LIGO interferometer, and you see it changing interference pattern on your detector. And obviously, this is exaggerated. It doesn't look like this, but it's the same idea, right? You change your arm length, you see a change in time. And basically, here you see the LIGO interferometer in Hanford in Washington State in the United States. There's another one in Louisiana. But basically, it's just this. Just one very powerful laser, actually, and a very large interferometer. And so this is what LIGO used to detect the first neutron star, or all the black hole mergers that it has seen so far. It basically uses this detector. And so this is the figure you saw before. Now you put in gravitational wave observations. They want the neutron star to have a bit lower radius. Then you can use also this electromagnetic constraints that go on top of this. But generally, if you put all of this together, you get a pretty good idea of what the radius of a neutron star is. However, uncertainties are still somewhat large, let's say, of the order of a kilometer, right, plus minus a kilometer. But we know a neutron star has to have this radius. Okay, but still, there are still sizable uncertainties. And I will talk about next how we get rid of those two. But are there any questions up to now?
I have a question.
Sure. Yes. Yes. No. So if they're chiral EFT breaks down around, let's say, 2 times saturation density, everything beyond that you cannot model based on this approach. you would need to do something else. Maybe if you do lattice QCD, it could tell you something about this. Or there are some other theoretical approaches, but they are not really effective field theories or something. So there's no systematic approach. I think the only way would be to solve QCD directly, and we cannot do this yet. This is why we have to do this modeling, because if we at some point know how the equation of state should look like, we still don't know why it looks like this, but we have a constraint what it should be, and then theorists can try to model this with some theoretical approaches. Thank you. Okay. Yeah, this is just everything together that you have seen before. So we go from this large uncertainty using only theory, folding in all these observations, and we get this smaller uncertainty that I just mentioned before. Okay. So there are two things you can use this for that are actually pretty interesting. So what you see here is the predicted radius of a 1.4 solar mass neutron star. And here you see, in the prior field, you see two results. This is if you use chiral EFT up to 1 times saturation density, and then you do this general modeling. This is if you use chiral EFT up to 2 times saturation density, and then do this general modeling. The posterior shows you what if you analyze gravitational waves. And you see that both of these priors shrink to the same posterior. And what you can infer from this is that chiral EFT up to 2 times saturation density is extremely consistent with what gravitational waves would predict, right? Because if you only used chiral EFT, you would get the same posterior, so you've only chiral EFT up to twice saturation density. You would get the same posterior as if you used it up to 1 times saturation density and you fold in gravitational waves, right? They look very similar. The change in the posterior here is from this one to this one is very small. So what this tells you is you can use these observations to test predictions of ab-initio theory, right? Because the neutron star, you integrate over all densities, so of course it matters what you do at low densities. And if you can calculate this, you can also, and measure, compared to measurements, you can use this to test chiral effective field theory. And we did some modeling where we used some Gaussian process approach to model the equation of state. And then we trained the Gaussian processes up to different densities on chiral EFT. So this is up to half times saturation density, up to 1 times saturation density, up to 2 times saturation density. So you get equations of state that probe chiral EFT up to different densities, right? They are constrained up to different densities. And then you can make your predictions for mass and radius. And you can fold in the observations and see what happens. What is the change in these bands, right? Are observations consistent with these bands? It could be that, for example, if you use chiral effective field theory up to 4 times saturation density, which you shouldn't do, but if you did, observations might just kill this, right? They might tell you this is penalized, you cannot do this. And so you would have information, no, you cannot take it up to 2 times saturation density. But it might be that that observations tell you, yeah, you should use it up to 2 times saturation density. So by an approach like this, you can try to test this. And actually, if you do this, you can see something like this. So here, this belongs, so this y-axis label belongs to this plot. What you see here is on this y-axis label. So it's basically the base factor of an equation of state set constrained with chiral EFT up to a certain density, versus a base factor, versus an equation of state set that doesn't know anything about chiral EFT. And then you can basically follow these curves, right? And you see, for instance, here, this is one chiral EFT calculation. If you trust it to higher and higher densities, your base factor goes up. So basically, nature tells you, yeah, it's much more likely that the equation of state set with chiral effective field theory up to a certain density is preferred. And then the difference between the blue and the black, ignore the yellow and the green, but the difference between the blue and the black one, which are 2 different chiral EFT calculations, tells you something about the uncertainty. Both of them are still preferred, right, over the unconstrained. So the base factors are much larger than 1. So both of them are preferred. But you see, for the black line, it becomes actually less preferable to use this calculation to constrain the equation of state, whereas for the blue line, it becomes more preferable. Okay, let's skip this. It shows you something about the interactions. So the difference is, It's a technical difference here. So the black line uses local interactions. They are usually softer. So they want, softer means lower pressure in neutron stars. They want smaller neutron stars. The blue line uses a different approach that uses non-local interactions. They want a larger pressure. So for the, for the data that was considered here, the black line was not preferred compared to the blue line because the pressure is smaller. However, okay, I wanted to skip this, but now I talk about it. If you change the data that you use to calculate the base factor, so here one data set is removed, then the situation changes. So if data wants you to have a low radius, calculations predicting a low radius are preferred. If data wants you to have a large radius, calculations predicting a large radius are preferred. Since data has large uncertainties, we don't really know which of the cases this is, and it really depends on data sets that you include. But in future, you will not have this problem because observations become more precise, and that's what I want to talk about in the last. How many minutes do I have? One? No.
No.
Okay, good.
I was just wondering, Ingo, about what you told in the first class that you can create moving the cathode, three-body forces by changing three-body forces. Is there an important impact when you move your cathode on what we can see so far?
I mean, you can move strength around, but I mean, you cannot eliminate three-body forces altogether, right? But obviously, you can move strength around. But if you usually do this, you do not only induce three-body forces, but you also change four-body forces, five-body forces. If you take all of this into account, it doesn't matter which scale you choose. But usually, I mean, everything I showed you is two and three-body forces, but there it's not, we don't do like a tuning of the cutoff so we can reduce the three-body force or something like this. But usually if you change the scale of the interaction, all many-body terms get affected, not just three-body forces. Okay, so the future. The future is very exciting. What you see here is like, this is an interesting LIGO plot. It tells you like the time of LIGO since it's turned on, right? So there's the first observing run where they observed the first black hole mergers. 02 is the second observing run in 2017 where they observed GW17817, which was the first neutron star merger. 03, they observed another neutron star merger, and currently we are in 04. And if you go to these different observing runs, you can see the sensitivity of the detectors improves. So this is basically indicated by this. This is the distance it can see out into the universe, right, in megaparsecs. So we increase our distance that we can look out into the universe, so our detectors become better and better. And you see there will be 05, most likely, hopefully. I mean, LIGO is NSF funded, so let's see what happens. But there will be 05 most likely in the end of this decade. So currently we're in the fourth observing run, where we haven't seen, unfortunately, any neutron star merger, or at least LIGO hasn't shared if they have seen a neutron star merger. We expected 7, and we saw 0, so maybe the rate of mergers is much smaller. But if you look at this plot, if we want to measure the radius of a neutron star, and we have, it's basically shown here with its uncertainty as a number of events that we see. And currently we're maybe here. So we have seen one event, and we get some uncertainty with some radius with some uncertainty. If we measure more and more stars, right, this uncertainty will become smaller. And so here you see different cases. It doesn't really matter, but you see that the uncertainties can be decreased by a factor of 2 just by having 20 events instead of 1. So if you just wait, we will get a better measurement of the equations of state that we are interested in. And here's a very nice plot that was made by the Syracuse group. So this is the set of equations of state I showed you before. They know about chiral FT at low densities, whatever, and then something else happens, but that's the uncertainty band. And let's say you pick 3 different equations of state, some that predict a larger radius, some that predict a smaller radius, and one in the middle. And here you see the measurement of the radius as a function of number of events. And you see it improves. If you have 300 events, you can maybe measure the equation of state, or the radius, sorry, with 1% accuracy. That's pretty nice. But then you can look at how many events do I have to see? How long at current merger rate does it last? Does it take to do this? And so here you see the number of events to get to a certain accuracy. I think it was 1% or 2% or something like this. So depending on the equation, if you have a large radius, obviously we need fewer events because 1% uncertainty is a larger number, right? So the change of radius is the absolute change is larger at 13 kilometers versus 10 kilometers. So if we wanted to measure the low radius equation of state to the same accuracy, we need 300 events. If you then use an optimistic or pessimistic or an intermediate scenario for the rate of mergers, you get here the number of years you have to wait to observe these events. So if we want, let's say, to measure the equation of state to 1% accuracy with current LIGO, we have to wait, and we're pessimists, we have to wait between 50 and 300 years. And no one wants to wait that long. And even if we're optimists, we have to wait between 3 and 25 years or something like this. That's awfully long. And we're most likely not in the optimistic scenario because we haven't seen the 7 promised neutron star mergers in the current observational run. So we are very close to the pessimistic scenario. And so we would need to wait hundreds of years to observe enough events to get to these accuracies. And that's very bad. So both Europe and the US have proposals for next generation gravitational wave detectors. The US calls it Cosmic Explorer. And here you see an artist's illustration of this. Europe calls it the Einstein telescope. I don't have a picture of this. But if you look at the sensitivity curves for these detectors, so this is the current LIGO, the blue one. Actually, this is the LIGO in 03, so then the current LIGO is somewhere in here. But if the highest LIGO upgrade is this LIGO A+, so that's as good as we can do in the sensitivity for the gravitational strain. And these additional new detectors, right, have a factor 10 increased sensitivity. So now you might think factor 10 is not that much, actually, but in gravitational waves it is a lot. Because gravitational waves, you measure the amplitude. So they go as 1 over r, not 1 over r squared. So if you do this, you can look out much further into the universe. So what you see here is, okay, the redshift can be related to the distance. So basically up here is the edge of the observable universe. And then you see the further out we go, we see different systems, right? Like all the neutron stars mostly live at these intermediate distances. The first black holes that potentially were ever made live very close to the edge of the universe, right? And then, yeah, we have all the other black holes somewhere here. The current detectors look somewhere down here. With Cosmic Explorer or the Einstein telescope, we can basically look to the edge of the observable universe in gravitational waves. We can see some of the first black holes that were formed. We nearly see all of the neutron stars that merge in the universe. So basically the curve, the sensitivity curve for Cosmic Explorer is this blue one, right? So this tells you which events can you see. And so, for instance, if we look at the one event we saw, GW 170817, which is down here because it's very close to us, we observed it with a signal-to-noise ratio of 30, which gave us these exciting constraints. Cosmic Explorer would have seen it with a signal-to-noise ratio of 3,000, so much, much more precise. It would have been like a 10-meter measurement of the radius if this would have happened, and we would have had Cosmic Explorer. So we can look much further out in the universe, and the signals we see will have much larger information, much richer information for us. And so if we had Cosmic Explorer, if we want to go to these accuracies, we do this within 1 year, no matter what the scenario is. Within 1 year, we will have all the information we need to pin down the radius of a neutron star to 1% accuracy. So that's extremely impressive. There will be hundreds of events per year that would give us this information. Okay. And so we can use this then. How much time do I have? 5 or 10 more minutes? Okay, 5. Let's skip this. So we can use this then, actually, to measure nuclear Hamiltonians. And I want to show you one example. So we have seen this in the first 2 lectures, right? We have our EFT Hamiltonian. It has some LECs. We can use our quantum mechanical solver. We get the equation of state. And then we solve the TOV equations, and we get neutron star observables. And in principle, if we use Bayesian inference, we can learn about our fundamental interactions again, right? So If we really wanted to do this, we need these next generation gravitational wave detectors. And we need to make this loop pretty fast, so we need machine learning and AI. And as I said, Casey will talk more about this on Saturday. But if you do this, let's say if you only focus on 3 body forces, you can do like a test case. So here you see the energy per particle as a function of density if we vary the 2 pi exchange interaction in the 3 body force, only in the 3 body force. So there are different low energy couplings. These are 100 different sets. We build an emulator for this. It's called the parametric matrix model. I will not talk about this here because you will hear about this on Saturday. But you can basically make curves where you just vary these 2 parameters in the 3 body force. And they give you also then some posteriors for this tidal deformability as a function of mass, so what actually gravitational waves would observe. So you can relate these 2 parameters to neutron star observables in an extremely fast way using machine learning. Then, if you do your Bayesian analysis of current data, you will get the following. You see one, which is one of these parameters you cannot measure at all. So basically, the prior is shown here as in purple, and then for different equation of state models, you see the posteriors. So prior comes in and prior comes out, so you do not measure anything. And in gray, you see the experimental number. So you see the experiment can measure C1 much, much more precisely. And this is the value we use currently in our calculations. So current astrophysics will not tell us anything here. For C3, it's a bit different. You get some information, but also not that much, right? So again, you see the experimental determination in gray, you see the prior, and you see astrophysics gives us some information. It wants this parameter to be rather small, but in the end, uncertainties are large. You are not at all competitive with experiment whatsoever. If you have 3rd generation detectors, the situation changes. So here, again, you see the prior on C3. Here you see this, what I showed you currently, the 90% posterior on C3 from this figure. So basically, it wants to be a bit softer, but no real change. Then, if you had Cosmic Explorer, so one of these 3rd generation gravitational wave detectors, and you would measure, you see, ignore the blue band, you see for the green band how your results improve on C3, right, on the parameter in the 3 body force. And with only 20 events in Cosmic Explorer, we get something, maybe it's still not as precise as the lab experiment on this parameter, but it's comparable in uncertainty, right? It's maybe a factor 2 better. So if we wait maybe 50 more events, we will be compatible to experiment in the determination of a low energy coupling in nuclear Hamiltonian. And I told you also, these pi-nucleon couplings are determined quite well. For nucleon-nucleon couplings, this might be completely different. Let's say if we have a coupling between 3 neutrons, it's very difficult to measure this in the lab. But neutron stars can tell us what this coupling looks like. And so this is, I think, a very exciting possibility to measure nuclear interactions using neutron stars. And I think that's pretty cool. Okay, so that's the end of my lectures. Here you see the people I want to thank. And in particular, I highlighted the early career scientists that actually end up doing all the work anyways. So they deserve our thanks. Obviously, the funding agencies too, most of them, that is, at least. And yeah, I thank you very much for your attention and for your many questions. And if you have more questions, please let me know. Thank you.
I think now after this nice talk, we should have some more questions.
I agree.
So please.
So I have a question concerning the determination of these LECs from these neutron stars. Shouldn't you, in principle, have, to vary all of them at the same time?
That's right. In principle, you should have to do this. So now, this was just an exploratory study where we froze the 2-body interaction. And then, because you could say, fine, I measured the 2-body. It is extremely unlikely that you get more information on 2-body forces from neutron stars than you get from 2-body scattering. Okay. So you can make the argument, well, yes, we freeze the 2-body force from experiment, and we only vary the 3-body force, which we learned from neutron stars, and this is what you find. But there is work that we do where we actually free up the 2-body force too, and we want to see, are there certain structures in the 2-body force you actually can determine from neutron stars? But that's a good question, yes.
Okay, thanks.
Of course, yes,
I
please.
C3, I don't remember, is the three-body force strength or C3? I don't remember well. C3.
Yeah,
Coefficient.
yes.
Is the three-body...
That's the, okay, both of them are three-body force. So in the two-pion exchange, you have two terms that go into neutron matter. One describes neutron S-wave interactions, three neutron S-wave interactions, which is the C1, and one that is much more important describes P-wave interactions between three neutrons, and that is proportional to C3. So these are both parameters in the three-body force, but one of them you see is not really measurable. It doesn't make a big change in neutron matter, but the other one does. But these are both three-body LECs.
And again, those are independent of the cutoff, or not?
No, but if you fix the cutoff, you will get a certain...
This is for a
Yeah, this is for a given cutoff, yes. Of course, they run with a cutoff too. So they would change. Yes. So that's all at a fixed cutoff. It's consistent, right? You cannot change, you cannot fit them and then later change the cutoff or something. You have to do it self-consistently. But here we freeze the cutoff at one value and then do the whole analysis.
Your model basically uses recurring EM.
That's right.
That your model is restricted to nucleons,
Yes,
right? So, but we know that neutron star may have different
right.
particles, right?
Yes.
So, how does that affect? Maybe your...
This is why we do this. Any particle you will have, any degree of freedom you put in, will give you one curve in the speed of sound with the speed of sound between 0 and 1. If you sample all of them, you sample every degree of freedom possible. I don't know, let's say if this blue curve, this one, the dashed one, is the true one in nature, I cannot tell you what made this curve look like this, but I know that this is the curve, and whatever degree of freedom exists in the neutron star will give you this speed of sound. So here we assume nucleons up to a certain density. Here in this plot, it's 2 times saturation density. It could be different. That's up to you. But everything beyond that, we just sample everything.
For instance, at the end, you mentioned about after many events of neutron star merger, you can determine equation state
Yes.
with 1% accuracy.
Yes.
But my question is, how does the other degree of freedom affect this 1% accuracy?
So, okay, from this point of view, whatever degrees of freedom there are, they will give you one equation of state, right? There's one equation of state in nature that all neutron stars follow. This is the one you measure. We model it in a general agnostic way. We don't know what degrees of freedom there are. We only know at low densities there are nucleons. That's everything we assume. Whatever happens at high densities, we don't assume anything. We measure the equation of state, and that's it. Then I gave, after, let's say Cosmic Explorer is on, I look at it for a year, I measure the equation of state to 1%. Some theorist has to tell me what happens at high densities, because I wouldn't know. But I know what the equation of state is. I just don't know what is there that makes this equation of state. So it's like a measurement of the pressure, right, as a function of density. But there can be many different ways to explain this pressure as a function of density.
Other questions? Student there, behind you.
Could you go back to the slide with this next gen detectors like precision?
Yes.
There was like for the European version for lower frequencies like less precision than for the US version. Is there a special reason for that?
Yes, there is. I don't know 100%. I think it's because, so the configuration is a bit different. I think the Europeans want to build a triangular detector that had different arm length, and Cosmic Explorer is like just large LIGO, and I think because of this comes from there.
Okay, because on the right side for higher frequencies it looks
They
like
are the
it's
same.
exactly the same, and
Yes.
then it's changing.
Yes. But so actually, for me or us or people who are interested in neutron stars, this frequency range is anyways the most important, right? Around 100 hertz, because this is where. So the information on this tidal deformability is maybe 50 to 300 hertz or so. This is where it's you can measure it. So there, both of these telescopes are pretty good. Down here, you would see maybe some black holes or something, which is also interesting, but I am personally less interested in black holes because they have no structure, really.
Thank you.
Shouldn't the equation states of the neutron star be different one from another because they may be from different proportion of neutrons and protons?
Very good question. If you have the same mass star that doesn't rotate, nothing, let's say they have the same magnetic field, it will be exactly the same equation of state. And they will have the same ratios of protons and neutrons because that's determined by fundamental interactions, right? So you have a certain fraction of protons and a certain fraction of electrons because the star will have a certain density, and then you'll have to look at the Fermi surfaces, right, and make that energetically consistent. But if the density is determined by the strong interactions of the neutrons. It's the same neutron, so they have the same mass in all stars. They have the same interactions in all stars. So at one mass, it will be exactly the same configuration. Now, if you change the magnetic field, things could change a little bit, but it doesn't have such a big effect on the radius. If the star rotates, you could have a slightly larger radius, right? Because the star gets deformed by rotation or something like this, right? So you could have effects like this. But if it's otherwise the same magnetic field, same rotation, and so on, they will all follow on the same line.
Okay, yes, it's my turn. Okay, so quite interesting. Now, so that you are in a strategy to include the Newton proton, but how about lambda and cascade? Because I'm one of the hypernuclear physicists, of course, and there are several in the color EFT and YN and YY interaction. Of course, in comparison with an interaction, still one interaction has a lot of degree of ambiguity. So then it's difficult to say and what kind of equation state we have. But so how is your opinion?
It's basically, I give the same answer I give here. So if you have hyperons, they will also give you some curve in the speed of sound. So
no difference. So that is curve. So that is curve, yes. So you were just talking about the electron and proton like this.
So,
yes.
So down there, so if hyperons appear, they appear at densities that are larger, right? They appear at twice saturation density. So they would be in this regime where we do this general modeling. So we would not have to model them explicitly. They are still modeled by this general approach.
Okay.
So if we knew the hyperon-nucleon interaction exactly, we could calculate where hyperons really pop up, what is their contribution to the pressure, and so on and so forth. So if we had the equation of state, we can learn about hyperon physics too, right? But this depends on the hyperon-nucleon models. And since they are not that good at the moment, we do not include hyperons. Yeah. But this approach should still cover them, because they are just another degree of freedom that does something, but it will still fall in this gray band somewhere.
Okay. Yeah, just as I understand it, you can, so if you have some so reliable the Y and Y interaction, you can do.
Yes.
Yeah.
So basically, too many slides, sorry. So basically, we could do something like this for hyperon couplings in principle. If we had some model for the hyperon-nuclear interactions, we do calculations. We can also try to infer their couplings, right? We could do this.
Okay. And
so you can learn these interactions from neutron stars, which is another exciting possibility.
That's right, yes. So, and in the future also, so you include this and Y interaction. In the
yes.
Okay, thanks.
I mean, it should be straightforward. Just someone has to do it, but yeah, fine.
Yeah, I just have the follow-up question to what Imo said. Let's say that you can change, you get more astro data. You can change like simultaneously all the LECs. Like, what could we learn? Let's say at the nuclear level, for example, about the discussion about Weinberg power counting or like Swedish power counting. Like, do you think we'll have a better way to understand like which power counting will be more accurate there?
Okay, perhaps is my answer. It depends really on what happens. So I don't know. There was a paper recently by the INT group. I don't know if you have seen where they say, there are 3 body forces that are at N5 LO in Weinberg power counting, but they should be at N3 LO or at N2 LO. If that was true, they will affect the equation of state. If they affect the equation of state, you will see this when you compare to data. So you can learn about these effects, definitely. So if there is like a prominent effect like this that affects something that actually does a considerable change in the equation of state, you will see it. If you think about some modification at leading order, you will not be able to map that out, because that will be a minor thing for the equation of state anyways. So it really depends on the modification of the power counting. But you could test different power countings, and at least you can say, yeah, we cannot distinguish them, or we can. So that's maybe interesting. I think that is interesting, not maybe. It's definitely interesting.
Okay, last question.
About the power counting. So it sounds like you need to finish the calculation to decide whether it's right.
Yes. Yes.
Is there some other ways?
No. Unfortunately not. So, I mean, Weinberg's way is a way where you don't need to finish calculation, right? You do just dimensional analysis, you write your Hamiltonian, you get something. But then we see this is not enough. But there are many people working in improving the power counting, but you always have to finish a calculation first. You cannot really a priori say that something is important or not, which is not maybe theoretically as appealing as it could be, but that's the world we live in, unfortunately.
We are estimating our uncertainty based on the truncated terms.
Yes.
We don't know.
Yes.
So if I don't calculate that, how do I know it's not important?
I mean, okay, when you do any calculation or any uncertainty quantification, you assume that your series at least is asymptotic, right? That's an assumption you make. If this wasn't the case, then you cannot estimate uncertainties, right? So we make this assumption. We see from the calculations that we did up to 4th order or 5th or whatever people do now, that it still works. So that we didn't find that it really breaks down, unless you really take the cutoff very large or whatever, then something happens in the power counting. But for most calculations that we do at reasonable cutoffs, everything works. So we haven't seen any indication that there's a really big problem. But this doesn't, I mean, if you assume Cayley of T does not at all converge and you have no idea what the next order is, then you cannot estimate uncertainties, right? Because then you basically give up. You say there's no way to estimate uncertainties. So at least you have to have this belief.
So thank you, Ingo. Thank you, Amor.
Thank you.